I'm really excited about this project, and it's something I've been working on for a couple of months, and so I'm just really happy to share it with you guys. So my name is Dibia. I'm a research engineer at Cloudera Fast Forward Labs. We have an office at Brooklyn, New York. And essentially, I spend half of my time researching, deploying technologies, and the other half helping clients build machine learning solutions. And then at night, I spend my time pretending that I'm an artist and I make art. Yeah. And so it turns out that if you do have neural networks, it can really help you do anything. And so the title of my talk today is Art plus AI, Generating Novel African Masks Using Generative Adversarial Networks. Cool. So just to give it a little background, why combine art and AI? And so for me, it's a little bit personal. I grew up in a West African country, and something that was really interesting when I was a little boy was that every year, at the end of the year, in December, our extended family will all travel to our village, and we'll spend about 2 weeks together. And so it was a fun period. And one of the highlights of that whole experience was that it was something called the masquerade dances. And so what would happen is that we're all in this square, or like the equivalent of a park, and you'll see interesting dressed individuals like this, and they dance really fast, and they have all these acrobatic maneuvers, and they jump around. And more importantly, they had these really interesting, elaborate masks. And so that was the first time I actually had some encounter with these masks, and since then, I've been really, really fascinated by them. And so fast forward to today, 20 years later, I am a machine learning engineer, and I really, really want to connect, to that aspect of my culture and my identity and my roots. But I'm not an artist. I can draw, and so what can I do? I can create artificial neural networks and kind of leverage that as an assistant to kind of like really, really explore and kind of find new interpretations of what African masks could be. And so to give a really fast primer on what African mask art are, here you see two pictures. On the left, you have a bronze mask. It's from a tribe from Nigeria. And on the right, you have another mask example, and it's from a tribe in the Congo. And one of the things, if you look at more examples, one of the things you'll find is that they have some interesting characteristics. And so immediately you find that they're fierce. And one of the reasons for that is because they are supposed to be representative of deities. They're supposed to be the spirits of the ancestors, mythological beings, or other beings that are believed to have power over humanity. Another characteristic of these masks is that they're pretty sophisticated. And so they're complex both in art, design, and the range of materials that are used. And so you see sometimes wood, really complex wood patterns are used to create these masks. Sometimes it's clay, sometimes it's bronze, and sometimes it's iron. And so there's a really wide range of materials that are used to create this mask. The third interesting thing about them is that they're surprisingly ancient. And so archaeological discoveries show that some of these pieces date as far back as the 9th century. And then finally, they are functional. And so they're not just artistic pieces that are created to be consumed for their visual excellence. They're actually functional. So much like you would wear a dress and you would like it to reflect your identity, that's pretty much in a similar way people would don masks, and it will be a really important expression of the identity. And so what did I do, and how did all of this come together to inspire this project? And so first of all, it's a way for me to kind of explore, engage with my culture, identity, and it's a way for me to bridge AI, art, and technology. So that's one of the motivations for this project. And another thing we probably have noticed is that there is an uptake in this area of generative art and art inspired by AI. But one limitation in this area is that most of it is characterized by classic European art. And so I thought, this might be an opportunity to diversify the conversation in this space. And then finally, if any of you work in the domain of generative modeling, you will find out that some of the data sets you find there are things like, Fashion MNIST, and CIFAR 100. And so there's opportunity to contribute more complex data sets that really help us push the limits of what generative modeling can do. And so part of this, the goals of this project is to, at some point, contribute a data set that enables more complex generative modeling. And so these are the main motivations for this project. And so before I go ahead, I'd like to show you guys some results. And so the entire panel you see here examples of none of these masks are actually real. And so everything you see here, all generated images and representations of what the neural network that I trained thinks an African mask could look like and could be. And I have a lot of favorites here, and I'll show you a couple of them as the presentation goes on. Okay, so just to give some background information on the process that I walked through as part of this project. So the first thing is that this project falls within the broader domain of efforts that have been termed as computational creativity, or generative art, or even code art. And so it's a pretty old field, it's an old area, and some of the incredible contributions here have been in terms of tools that are used in this domain. So how many of us have used P5.js? Okay, cool. Processing, cool. So yeah, awesome. And so for most of these tools, the intuition here is that you have an idea of some art you want to create in your head, and you write some code and then you bring it to life. And so some of the patterns you see in the background, these are all generated by procedural code that goes ahead. Based on your instructions, based on your code, you generate some bit of art. But neural network kind of changes this paradigm just a little bit. And so neural networks are a class of software that allow machines to learn rules directly from data. And so as opposed to tools like P5.js for processing, imagine if you wanted to draw some circles in P5.js, you would write a few lines of code. And so if you want to do the same with neural networks, rather than writing code, you actually go and gather images. And so in this case, your image data becomes the code that you actually, the image data becomes the source input to your network, and then your network generates the code. So why would we want to do that? And so if we wanted to generate simple stuff like the patterns we see at the back, it's easy to actually write code to do this. But if you actually want to write code that generates African mask, and not just that, you want stuff that's kind of novel and new, how would you go about writing code like that? You probably can't. And so for this, you actually need neural networks that help you kind of imagine this process. And so when I started working on this project, I kind of split it into 3 simple parts, which is the basic data science process. And so the first interesting part is curating the data set. The second part has to do with training the model, making decisions around what kind of GAN architecture do you use, how do you set your hyperparameters, what kind of resolution do you want to generate. And then finally, there's some work put into evaluating the results, and then interpreting what the neural network has come up with. And so for dataset curation, I guess like one of my previous speakers mentioned, this is the most interesting, most amazing, most delicious part of the process, right? And so I started with data scraping code, manual image downloads, and so I started with at the end of this process I had about 20,000 images. And then I went through the process of careful hand curation. So this involves removing vector images because we want realistic images. This involves removing incorrect content and masks that have nothing to do with Africa. Then finally removing a bunch of duplicates. And at the end, I was left with about 11,000 curated images. And so this process takes a bit of effort. It took a couple of weeks to actually carefully curate and kind of like get the data set in a condition and a manner that I was comfortable going ahead and using it to train my neural network. And so once I had all my neural network data, once I had all my data available, the next interesting thing was to identify the right model to use. And for this, I used something called the generative adversarial network, and so which are also called GANs. And so GANs are a really interesting arrangement of 2 neural networks. So on one hand, we have something called the generator, and on the other hand, we have something called the discriminator. And so on the right, you have an image that kind of describes what the generator looks like. And so what it does is that it's a feed-forward network. It takes in a bit of fixed noise, and the output of that process is that it generates an image. And so the goal is that as the model is trained, you want it to take in this noise vector and generate an image that actually looks like an actual mask. And so the second part of this model is something called the discriminator, and it has a simple task. And so here its goal is to take in an image and tell if this image is actually real or it's fake. Fake in this sense being something that was generated by the generator, something that really didn't come from a training data set. And believe it or not, it turns out that if you structure these two networks together and you get them to play a game, at the end of that process, you actually have a generator network that has learned to come up with images that look plausible. They look like they're actual masks. And you have a discriminator network that has learned to become really, really good at telling fake from real. And to describe this whole process, I like to tell this really funny story of the police and the forger. And so the story is like this. First, the forger starts as an amateur. And so his task is to create art that looks like, let's say, Van Gogh or Rembrandt. And he wants to sell it and make profit. But because he's really not good at this process, once he tries to sell the art, the police comes and says, hey, that's a fake, you're going to jail. And so this guy is caught, he goes to jail, there he meets the Godfather, and the Godfather tells him, oh, this is the reason why you were caught, and then he gets better, and he gets out of jail, and he makes even better fakes. And at the end of this process, the forger gets really good at creating fakes that the police can detect. And at the end of this process, if the police does his work correctly, he becomes even better at distinguishing fake from real. And so this is pretty much the process that a GAN actually goes through. And at the end of the process, we're really interested in the generator, such that when we're done with the training process, we can actually give it some random noise, and it gives us some new mask image that looks interesting and looks like it's a part of the training data distribution. Okay, and so I have a little video on the left. Looks like if it's not loading up right now. But what it was going to show you was an example of what the training cycle looks like. And so initially what you would see is that each of the boxes starts out as random noise. And so the generator has very little skill at that process. But as we go through various epochs, you will find that it actually starts to come up with stuff that really looks like masks. And so there are a few processes I went through in order to actually train this model. And so I started out with a sample DCGAN TensorFlow implementation. And so DCGAN stands for Deep Convolutional Generative Adversarial Networks. And so if you're working with images, in this case I'm generating images of masks, it's really important that you use your generator and your discriminator actually have convolutional layers. And so a DCGAN is just one formulation of a GAN that allows you to generate images. Along this process, one of the challenges that I faced was that I had to write my own custom data input pipeline, and one of the issues that came up was there were some differences in how I had generated my data set compared to how the code was actually expecting the image data to look like. And so when each of us here process images, how do we specify that length, height, width, and channels, or channels, height, and width? Which one do we use? Channels at the end or channels in front? Any preferences? Okay. So typically, I usually, for a given image, I specify the height, the width, and then the number of channels. However, at some part in the sample code I found, it was actually channels first, height, and width. And so what that just meant was that the way the model was consuming the data was wrong, and all of the first 100 experiments I ran just didn't work well. And so one thing you really should do is to validate your data format, and so that will really save you a lot of pain. Right. And so the other thing I did was that the sample code I found was it was designed to generate 32px pixel by 32 pixel images, and so I just had to modify the generator and the discriminator such that it learns to generate higher resolutions. That's 64px and 128px. And then finally, you wrap all of this into an experiment, a couple of files, Python files. In this case, I trained with a TPU, and I'll get into a bit of rationale for why TPUs work well for a problem like this. And so you set up your TPU instance, and then you get your data into a GCP bucket, and then finally you run your training. And so it turns out that setting up a TPU is a fairly straightforward process. There are two interesting things that you need to do. So the first thing is you need to set up your project, set up your zone data. You need to enable TPUs for your GCP project. And once you do all of that, you use the cTPU command line tool. Essentially, you run cTPU up, and essentially what it does is that it sets up a compute engine virtual machine and allocates some TPU resources where you can actually run your training. And so once you're done with that, you could, in this case, this is the code I just used to spin up my training process. And so here you set an environment variable that mentions your GCP bucket name, and then the name of your TPU, and this again main is the name of the file that actually runs my training. So it's a fairly straightforward process, and it's kind of easy to implement. And so why TPUs? So the first value here is that it's easy to set up, it's fast, and it turns out that GPUs are available. And so if you're here in the room and you would like some guidance on how you can go ahead running training jobs on TPUs, I'm happy to discuss with you a little bit more on that. And it turns out that they're really fast, and so you could use them as individual TPUs, or you could use them in a pod formation where you could use 8 or 16 TPUs. The main limitation here is that you need to rewrite your code such that it takes advantage of the TPU architecture. And so this process it's not always obvious to a lot of developers, because your basic TensorFlow code or your Keras code might not run just as is on the TPU. You actually need to write some code that gets your application to run on TPUs. And so right now, the way you do that is to use TPU estimators, which are a little harder to work with. They're less friendly than Keras or TF 2.0. And so I know that there's some work in progress to allow GPU support for TF 2.0 in Keras, but as at the last time I checked, I don't think that's available yet. And so at this point, I should be really happy. I have some results. I'm able to generate some images. But one thing that I actually did notice was that because of instabilities in training again, some of the best results I got were with just the 64 pixel configuration. So for 128 pixels, there's a known problem with training GANs called mode collapse, where your GAN just doesn't generate a variety or a lot of different images. And so what can we do to actually address this issue? And so it turns out that we can use something called super resolution GANs. And so these are another formulation of GANs where you have your generator, rather than taking in a random noise vector and then generating an image. What it takes in is that it takes in a low resolution version of an image, and it learns to generate a high resolution version of an image. And so the question is, does this work? And so I'm going to show you some of my favorite examples. And so on the left here, we have a 64 px image, something that was generated by the model. And then we pass this to a super resolution GAN. In this case, it's a GAN trained within a product called Topaz Labs Gigapixel. And on the right, we have a 378 pixel output. And so you will notice here that actually there are some details that just don't exist in the 64px image, but now they're actually available in the 378 pixel image. And it's pretty much like magic. And so the neural network here has kind of performed another stage of interpretation where it has hallucinated some details that look like they fit into the resulting super resolution image. And so this is another example: super low resolution on the left, high resolution ESR GAN results on the right. So this is one more example. So some of my favorite examples curated. I guess the only thing I haven't done at this stage is to name them. What would be a good name for this guy? Sad face. Yeah, I'll take out some time and name them. And so those are some of the interesting things. And so at this point, I have high resolution images. And so the researcher in my head is, how novel are the images that were actually generated by this mask? Did it really come up with stuff that's new? or did it just copy some stuff from the training data set? Did it mishmash stuff together? I really want to know, and I want to find ways to actually explore, what the GAN has actually learned. And so to do this, one thing I did was that I built a tool that helps with algorithmic art inspection. And so basically what I do is that I use concepts from semantic image search, and for each of the generated images, I use a pre-trained model to extract some features, and then using the same pre-trained model, I extract features from all the images in the data set. And that way, for each selected image, I can then go ahead and say, for the image that I have selected, and so for this image that I've selected, which was generated, these are all the other images in the data set that look the closest to it. And so the good news is that I didn't see cases where the neural network had just done verbatim copying. It actually generated stuff that was substantially different, just not as smooth and as clean as what we have in the original data set. And so this sort of algorithmic inspection also enabled other things. And so it enabled me find specific types of modes that the GAN had learned. And so in this case, it's oblong mask images. And so the GAN had learned to generate masks that had this oblong shape. In some other case, it had learned to generate masks that had like hair or hair-like projections. And in some other places, it learned to generate oval masks. And so this is towards the end of my presentation. And so what are some reflections on things that I thought were interesting and open questions that arose as I worked on this project? And so the first thing that I think is that, as algorithmic art, generative art becomes more popular, I think we need more tools that allow us to actually inspect the novelty and visual quality of what's being generated. And so, yes, we have AI as a partner that's helping us create art, but it's also important that we have metrics and tools that help us evaluate, is this stuff really novel? If Picasso was alive today, would he be disappointed by what we're calling art or not? I guess that's a discussion for another day. And so the second thing that arises frequently is who has agency, right? And so the stuff that's generated, is it mine? Or is someone going to sue me some years down the line and say, this stuff belongs to the machine, the generative adversarial network? And so there are a lot of conversations around that. My thinking is that the process of curating the data set is some form of art, and so that only comes from the artist, which turns out to be me. The process of identifying the right hyperparameters that give those really nice, cool images, that also comes from the artist, which turns out to be me. And then finally, who names the art? I name it, and I also kind of interpret and explain what the meaning is to the rest of the world. And so I think in this way, the artist retains some kind of artistic contribution, and the machine, is just an assistant. And so there's also ethical issues that arise. It's important that artifacts generated from this project are used in a way that's inclusive of its origins, the sources where it came from in West Africa. It's important to think of best practices around the distribution of these data sets and every other emerging concerns. And so for some next steps, conditional generation, can we say, give me a mask that came from Congo, or give me a mask that's from North Africa? And so there are ways to inject this kind of information to the training process such that we can perform this kind of condition generation. How can we improve the quality of generated images? There's some papers, especially the paper on the relativistic GANs, and so that's one potential approach there. And then finally, I'm working on an interactive tool for navigating the latent space of all the images that have been learned by these GANs. So that could be a potential interactive installation. And so if you're really interested in this sort of work, I actually have some sample code. If you go on GitHub, you actually can get your images. The code will actually help you generate TF records from the images, and it will help you generate a 64px or 128px GAN that generates this kind of images. And so I've written some blog posts and also this algorithmic art inspection interface, and you can find all of that there. Thank you.